Study Section 9, Introduction to Web Programming. Concurrency Programming for the Web. Introduction. In the previous study session, we learned how to use Hypertext Preprocessor (PHP) to create dynamic web pages by adding various functions like sending email, sharing data from page to page, etc. to our website. In this study session, we'll discuss how an operating system manages multiple requests by the same user without having to have multiple copies of the programming running in the computer. Learning outcomes. When you have studied this session, you should be able to 1. Use concurrency, 2. Use thread, 3. Express multi-threading, create threads. Concurrency. If you have a multiprocessor or a distributed system, you will have concurrency. Since in these systems, there is more than one CPU executing instructions. Similarly, most hardware has separate parts that can change state simultaneously and independently. But suppose your system consists of a single CPU running a program, then you can certainly arrange for concurrency by multiplexing the CPU among several tasks. But why would you want to do this? Since the CPU can only execute one instruction at a time, it isn't entirely obvious that there is any advantage to concurrency. Why not get one task done before moving on to the next one? There are only one possible reasons. 1. A task might have to wait for something else to complete before it can proceed. For instance, for a disk read. But this means that there is some concurrent task that is going to complete, in this example, an I/O device, the disk. So we have concurrency in any system that has I/O even when there is only one CPU. 2. Something else might have to wait for the result of one task but not for the rest of the computation, for example, a human user. But this means that there is some concurrent task that is waiting, in the example, the user. Again, we have concurrency in any system that has I/O. In the first case, one task must wait for I/O and we can get more work done by running another task on the CPU rather than letting it idle during the wait. Thus, the concurrency of the I/O system leads to concurrency on the CPU. If the I/O wait is explicit in the program, the programmer can know when other tasks might run. This is often called a non-preemptive system because it has sequential semantics except when the program explicitly allows concurrent activity by waiting. But if the I/O is done at some low level of abstraction, higher levels may be quite unaware of it. The most insidious example of this is I/O caused by the virtual memory system. Every instruction can cause a disk read. Such a system is called preemptive. For practical purposes, a task can lose the CPU at any point, since it is too hard to predict which memory references might cause page fault. In the second case, we have a motivation for true preemption. We want some tasks to have higher priority for the CPU than others. An important special case is interrupt, discussed below. A concurrent program is harder to write than a sequential program, since there are many more possible paths of execution and interactions among the parts of the program. The canonical example is two concurrent executions of x semicolon is equal to x plus 1. Since this command is not atomic, x can end up with either 1 or 2 depending on the order of execution of the expression evaluations and the x semicolon is equal to x plus 1 assignment. The interleaved order evaluate x plus 1, evaluate x plus 1, x is equal to result. X is equal to result leaves x is equal to 1 while doing both steps of one command before either step of the other leaves x is equal to 2. This is called a race because the two threads are racing each other to get x updated. Apart from recent hardware trends towards multi-core and multiprocessor systems, the use of concurrency in applications is generally motivated by performance gains. There are three different fundamental ways on how the concurrent execution of an application can improve its performance. Reduce latency. A unit of work is executed in shorter time by subdivision into parts that can be executed concurrently. High latency. Multiple long-running tasks are executed together by the underlying system. This is particularly effective when the tasks are blocked because of external resources they must wait upon, such as disk or network I/O operations. Increased throughput. By executing multiple tasks concurrently, the general system throughput can be increased. It is important to notice that this also speeds up independent sequential tasks that have not been specifically designed for concurrency yet. The presence of concurrency is an intrinsic property for any kind of distributed system. Processes running on different machines form a common system that executes code on multiple machines at the same time. Conceptually, all web applications can be used by various users at the same time. Thus, a web application is also inherently concurrent. This is not limited to the web server that must handle multiple client connections in parallel. Also, the application that executes the associated business logic or a request and the backend data storage are confronted with concurrency. Multithreading. Threads are lightweight processes. They share the same address space. In multi-threaded environment, programs make maximum use of CPU so that the idle time can be kept to minimum. The main purpose of multithreading is to provide simultaneous execution of two or more parts of a program to maximum utilize the CPU time. A multithreaded program contains two or more parts that can run concurrently. Each part of such a program called a thread. Each thread has a separate part of its execution, so this way a single program can perform two or more tasks simultaneously. There are several thread states. A thread can be in any one of the states at a particular point of time. It can be running state. It can be ready to run state as soon as it gets CPU time. A running thread can be suspended. A suspended thread can be resumed. A thread can be blocked when waiting for a source. At any time, a thread can be terminated. Handling of multithreading in Java is quite simple. A thread can be created in two ways. 1. By extending thread class. 2. By implementing runnable interface. Method 1. Thread creation by implementing runnable interface. 1. One way of creating a thread is to create a class that implements the runnable interface. We must need to give the definition of run method. 2. This run method is the entry point for the thread, and thread will be alive till run method finishes its execution. 3. Once the thread is created, it will start running when start method gets called. Basically, start method calls run method implicitly. A simple example, class multithreading demo implements runnable public void run system out print in my thread is in running state public static void main string args multithreading demo opt is equal to new multithreading demo thread t opt is equal to new thread opt t opt dot start output my thread is in running state. Method 2. Thread creation by extending thread class. This is the second way of creating a thread. Here we need to create a new class that extends the thread class. The class should override the run method, which is the entry point for the new thread as described above. Call start method to start the execution of a thread. We will explain this method by using the same above examples. Example 1. Class multithreading demo extends thread public static void main string args multithreading demo opt is equal to new multithreading demo public void run system.out.println my thread is in running state opt.start output my thread is in running state. Study section summary. In this study session, you learn that 1. A web application is also inherently concurrent because all web applications can be used by various users at the same time. 2. Threads are lightweight processes. 3. There are several thread states: running state, ready state, suspended state, resumed, blocked, waiting, terminated. A thread can be created in two ways: A. By extending thread class, B. By implementing runnable interface. This is the end of study section 9. Thanks.